In today's lesson, we are going to be looking at some circle properties. So we're just going to be looking at some of the kind of geometric properties that can kind of come into play when looking at circles, specifically with some angles. So looking at angles and circles, if we look at angle BAC, so BAC is this angle here. I'll highlight that. So that angle there, that's considered the central angle. And angle BDC is considered the inscribed angle. And if you're reading this, the BDC and BAC, how do you figure out how it goes? Well, you start at point B, go to point D, and then go to point C. That's how you can kind of read that notation, or that middle letter, or that describes at what vertex the angle is at. So in terms of the inscribed angle, D is the vertex that the angle's at, so it's in the middle of our terminology. So this inscribed angle is the angle that is formed in the interior of the circle when two chords intersect on a circle, or on the circle. So if we think of the circle as this part, this entire, well, obviously the circle, we look at the interior, right? The two chords meet, these two lines meet on the circle. The inscribed angle is going to be the angle that forms from those two intersecting lines. And now, how do the central angle and the inscribed angles compare? So we'll zoom in, you can kind of see how they compare. How do these two angles, A and D, how do they relate? Take a look at them. How do they relate? Well, by looking at these ones, in this picture, it looks like the central angle is double, or 2 times, the inscribed angle. And now we're going to look at kind of a digital manipulative, and we want to see if I drag point B around, does that relationship still hold true? So if I move angle B around, right, even if I go down here, is the central angle, this angle here, still double the inscribed angle? Now, obviously, in this case, it's no longer the same scenario, so I have to at least go here. Does that hold true? And it does. It does seem to hold true. If I move point B around, yes, it holds true. So let's kind of put it back a little bit close to normal. If I move point D around, does the inscribed angle change? So depending on where I move point D, obviously I move it to the other side, that becomes something different. But if I move it around, is that angle changing? No, it's not. So it doesn't really matter where point D is in terms of, as long as two chords are meeting somewhere on the line. In this case, again, it's something different. If we were to look at the other side, it might be double. But again, anywhere where we still have our chords, does the inscribed angle change? Yes, it does, but only when we rotate it past point C or D. So as long as we're keeping it in the similar, this kind of this kind of format or this kind of shape. And sometimes this is called kind of like the Star Trek pattern, because we can kind of see this kind of forms the kind of shape of a Star Trek badge. If you ever watched Star Trek, you might kind of see the comparison. So as long as we keep it kind of like this, or an arrow, that kind of shape, the angle D will not change, and it doesn't matter how we move B or C. Again, as long as we're not going past the specific point or the other point, then that relationship of the central angle being double the inscribed angle holds true. The next scenario we're going to look at is when an angle is subtended by a diameter. So, well, what does that mean? Well, angle A, B, and C is the inscribed angle. So again, this is looking at ACB, our 90-degree angle. And since the chord, or basically a line going from one side, or touching one side of, or touching two parts of the outside or the rim of our circle, so since this chord here is the diameter, or it's going through, we can say that this angle ABC, or sorry, ACB, is subtended by a diameter. Basically, it's closed off. Right, so we have this 90-degree, it's closed off. Those two lines are connected. The two lines that form that angle are connected to make the diameter. So we want to know what happens to the right angle if I move point C. So if I move point C around, what happens? Well, let's go to our digital manipulative. And if I knew, oops, we want to keep that here. If I move point C around, well, what's happening? Now, we want to be careful, because even though it's flipped around and it says 270, if I still look at angle C on the inside, that's still 90. It's just a matter of how or what the program is looking at. It's looking at the reflex angle. We want to be looking at just the opposite, which we can see is 90 degrees. So we can see that as if our two chords, or if our angle or inscribed angle is subtended or closed off by the diameter, these two lines, or the angle, is going to remain 90 degrees. Obviously, if we go and we line it up completely on one of the other points, B or A, we no longer have any angle because we're forming a straight line. A little bit of an error in the program, or it's assuming that I'm not quite on A or B. That's where we're not seeing it change to 0. But the main thing is that if our inscribed angle is subtended or closed off by the diameter, let's just draw that in again. What happens to the right angle? Well, it stays 90 degrees. Wherever we move it, again, unless we're forming a straight line, that angle on the inside is still 90 degrees. Let's take a look at another property. Let's take a look at a perpendicular bisector of a chord. Well, a lot of new words here. So what does all this mean? So if two lines are perpendicular, it means they intersect at a 90-degree angle. We've talked about perpendicular lines before, if you remember back to the linear relationship unit. So perpendicular lines meet at 90 degrees. BC is a chord. Right, so BC, that line segment here, is a chord. It goes from, it touches the circle at 2 points on the rim. D is our midpoint. So D is our midpoint. It's the halfway point. So that makes either side the same length. Now, if a line is drawn perpendicular, so we see that line is being drawn perpendicular, right, because it meets at 90 degrees. That's why we have that square there. It goes through that midpoint. So a line that's drawn perpendicular to the chord through that midpoint, this line is called the perpendicular bisector, or right bisector, for two reasons. Perpendicular means 90 degrees. bisector means cuts in half. So it cuts our line in half and it crosses at 90 degrees. Now we want to note that the perpendicular bisector goes right through the center of our circle, point A. So in this diagram, it goes right through the center. Now what happens if we move point C or point B? Does the perpendicular bisector still go through that point? Well, let's go to our investigation. Let's take a look. If I move point C around, nope. It seems that it doesn't matter where point C is or point B. Sorry, just having a little fun with this. It doesn't matter how it's located. If I move one of those points or any chord that's met with a perpendicular bisector is always going to run through the center. So again, that's one of those properties, right? If you want to find the center of a circle, you have a line, draw one line across from the other, draw a 90-degree line that bisects that chord, and somewhere along that line, you're going to find the center of the circle. So, does the perpendicular bisector still go through point A? Yes. It always goes through the center. So yes, it doesn't matter if I move point C or point D anywhere around the edge of the circle, it's still going to go through the center. Or that perpendicular bisector, sorry, is still going to go through the center. Lastly, we're going to look at inscribed angles subtended by the same arc. So subtended meant that we closed it off, or we kind of connected the two lines that formed our angle. So if we look at angle CDB, I'll highlight them just to make it a little easier, CDB and CEB, they are subtended by the same arc. So what that means is if I look at angle CDB or angle D, just to make it a little bit easier, the two chords that make up that angle are connected by an arc. We can see highlighted in yellow. And angle E, the two chords that make up that angle are also connected by that same arc that angle D was subtended by. So what do we notice about the two angles? What's unique about them? Well, taking a look at them, right, we can see that they're the same. The same, or they're equal, however you want to word it, both 38 degrees. Now we want to look at if I move point C, if I move any part of the arc, is it going to change the angles? Or what's going to happen to the angles? Are these properties, is this property going to stay the same, or is something going to happen? So again, let's go to our interactive. Let's move point C first. So let's move part of this arc. And we can see the angles are staying the same. If I flip it on the other side, it's essentially the same thing. But if I move point C, obviously if I move it on the other side, it's no longer the same arc. So I need to keep it on the outside of point D and point E. But if I move C, I can see that those two angles are still staying the same. Same thing with B. So if I change the two endpoints of that arc, it doesn't change the property. The property still stays the same. So changing the endpoints on the arc does not change the property, which means the two angles are equal. Now the next part is, what happens if I change point D? So if I move point D or point E, let me just move this up a bit. Moving point D or E does not change the angle at all. So while moving the arc, or moving the endpoints on the arc, does change what the actual angles are, it doesn't change the property in that they're equal. It does change them though. However, moving at either of the angles, or either of the points, the vertexes or the vertices that form the angle, it doesn't change the actual measure. So the measure stays the same for these angles. It doesn't change. So if I move the points, or that middle point, or the point where the angle occurs, that vertex, it's not going to change the actual measurement. Changing the endpoints of the arc will change the measurement, but it's not going to change the property, which is that the two angles will be equal. Again, just some unique properties that we might see occurring with circles. You might also think about, well, if these two angles are equal, we know that opposite angles are equal. So these two ones, use a different, so say x and x, those two are equal. That must mean then that these two ends are equal. Golden dot. So basically we have two similar triangles in the sense that the angles are the same. So again, just some kind of unique properties of the circles that you may come across that will help in terms of determining missing angles depending on different scenarios that you may come across or different questions.